Welcome back to the deep dive. Today, we are cracking open what feels like a secret rule book for network operations. The sources you sent over are just phenomenal. We're getting right into the weeds of advanced certification material.
Oh yeah, this is JNCIP level stuff, the kind of thing that trips people up in the real world, not just on an exam.
Exactly. So our mission here isn't just to, find the right answers. It's to pull out the bigger architectural ideas. We want to understand why these rules are so strict.
Why things fail when they look like they should work.
Yes, why a packet just vanishes, or why scalability and isolation seem to be in this constant fight. It's really a shortcut to understanding the DNA of modern networks.
That's a great way to put it, because if you've ever configured something perfectly and it still doesn't work, the answer is almost always in one of these tiny specific constraints we're about to talk about.
Okay, let's jump right in with a rule from ISS that feels, well, surprisingly brutal. It's a case where everything on the surface looks totally fine.
I think I know which one you mean.
So imagine you've got two routers, A and B. They're sitting right next to each other. A cable's connecting them.
Physically connected, yep.
Both are configured as level 1 routers, only level 1. But here's the twist. Router A is in IS area 49.0001, and router B is in area 49.0002.
Different areas.
So what happens when they try to talk to each other?
Well, what happens is nothing. They will not form an adjacency at all. The correct answer is just a total failure to communicate.
But wait, they're directly connected. They're both running ISIS. Why the silent treatment?
It comes down to the most fundamental rule of level 1 routing. It is designed from the ground up for intra-area routing only.
So only within its own little neighborhood?
Precisely. Its entire job is to handle traffic inside one area and then pass everything else off to a level 2 router, which is kind of like the designated exit door for the area.
I see.
So if a level 1 router sees another level 1 router trying to connect from a different area, that mismatch is an immediate deal breaker. The protocol basically says, you're not in my area, I don't talk to strangers, and that's it.
So you get no neighbor relationship, no hellos, nothing.
Absolutely nothing. It's a very clean, but often frustrating failure. It shows you that networks are built on strict logic, not on what seems flexible.
Okay, that's a perfect example. Let's pivot to BGP now, where the logic isn't about connection failure, but more about intentional information loss.
Or filtering, yeah.
Right. I'm talking about BGP attributes and this idea of transitivity. Let's focus on the multi-exit discriminator, the MED. Why is it classified as non-transitive?
The MED is so important for traffic engineering, but that non-transitive part is what keeps the internet, stable.
What does that actually mean in practice, non-transitive?
It means the attribute has to be stripped from the route update before it gets passed along to another external peer. So let's say AS100 sends a route to its neighbor, AS200, with an MED value.
Okay.
AS200 uses that MED to decide how to send traffic back to AS100. But, and this is the key, when AS200 then advertises that same route to a different neighbor, say AS300, it removes the MED.
So it's like a secret just between the first two. It's not for public broadcast.
Exactly. It's a whisper for your immediate neighbor.
Yeah.
And the reason for that is critical. The MED reflects a cost or a preference that's only relevant to the AS that sent it.
Ah, so it wouldn't make sense to AS300 anyway.
Right. If that MED traveled globally, a tiny preference from some small network could ripple out and cause weird routing decisions halfway across the world based on totally irrelevant data. Stripping it keeps local problems local.
That makes perfect sense. It's all about controlling the blast radius of your own policies.
Yep.
Okay, sticking with BGP, let's talk about confederations. This is a tool to solve that nightmare of a full IBGP mesh, right?
It is. You break one huge AS into smaller private sub-ASes.
So when a router inside this complex internal structure needs to talk to the outside world, what AS number do those external peers actually see in the AS path?
And that's the beauty of it. To the outside world, they only see the main public AS number, the confederation ID. All that internal complexity, all those little private AS numbers you've created, they're completely hidden.
So you're masking the complexity.
You're totally masking it.
Sure.
If you didn't, the AS path would get super long and confusing, and that could mess up path selection for other networks. By hiding them, the confederation just looks like one single normal AS to everyone else. It's a brilliant way to scale internally without breaking the external world.
That's a massive scaling win. Okay, let's look at another complexity reducer, OSPF snub areas. They're designed to shrink the link state database. So when an area border router, the ABR, is guarding the entrance to a stub area, which specific LSA type does it block?
The one that gets stopped right at the door is the Type 5 LSA, the external LSA.
And the Type 5 is carrying all the information about routes from outside of OSPF, right? Like from BGP or somewhere else.
Exactly. And that can be a ton of information. If you're connected to the internet, you could be flooding thousands of external routes into your OSPF domain.
Which would bloat the database on every single router.
And crush their CPUs. The whole point of a stub area is that the routers inside it don't need all that detail. They just need to know the way out. So the ABR blocks all that Type 5 noise and just injects a single simple default route instead.
You're trading detailed visibility for efficiency.
It's a classic trade-off. You get stability and a much smaller resource footprint.
That's a perfect segue, actually. Let's bring that same fight isolation versus convenience down to layer 2.
Right.
Private VLANs. PVLANs are the absolute definition of isolation. So if a host is plugged into an isolated port, who is the only entity it's allowed to talk to at layer 2?
The rule here is just ironclad. That host cannot talk to any other layer 2 device. Not another isolated host, not a community host.
Yeah.
The one and only destination it's allowed to reach is a promiscuous port.
That sounds incredibly restrictive, like it's almost antisocial. Why so extreme?
Because that's the whole point. The design goal is zero lateral communication. Think about a public cloud provider. You can't have one customer's virtual machine snooping on another customer's traffic.
Okay, that makes sense.
The promiscuous port is the designated exit. It can talk to everyone, and it's almost always the default gateway, a firewall, or some shared resource. So the isolated host can get out to the internet, but it can't move sideways to poke its neighbors. It's ultimate security enforcement.
Right, for those highly regulated or multi-tenant environments. But what about devices that just can't play by modern security rules? You know, legacy printers, IoT sensors, things that can't run an 802.1x client.
The messy real world.
The very messy real world. How do you authenticate them without forcing users through a captive portal every time?
Yeah, that's where we get into the workarounds. The solution is M-Radius, sometimes called M-Authentication Bypass.
So you're using the M address itself as the credential.
That's it. When the device connects, the switch grabs its ME address and sends that to the Radius server as the username and password, basically. If that MAC is on the approved list, the server tells the switch to open the port.
It's a clean way to apply policy to devices that can't participate in the policy themselves.
Exactly. It's a vital tool for bringing all that operational tech under a unified access control policy without having to, replace every printer on campus.
A clean solution for a messy problem. I like that. Okay, moving on to efficiency. Layer 2 multicast. It's famous for just flooding everywhere if you let it. What is the main job of IGMP snooping on a switch?
Its main job is to save bandwidth. Pure and simple. Without it, multicast is just broadcast in disguise.
What do you mean?
Well, think of a high-definition video stream on your network. Without snooping, the switch would flood that stream out of every single port in the VLAN, whether there's a device there that wants it or not.
Which would just destroy your network performance.
It would saturate everything. IGMP snooping makes the switch intelligent. It listens for which devices actually ask for the multicast stream, and it only forwards the traffic to those specific ports.
So it constrains the flood?
It turns a fire hose into a set of targeted water fountains. It's absolutely essential for any network doing video or multimedia.
Okay, let's talk hard limits now. Sometimes you can't just scale forever. You hit a wall. So if an engineer is building a network with VSTP VLAN spanning tree protocol, what's the specific ceiling on Juniper platforms before they have to migrate to MSTP?
They will hit a very, very hard ceiling at 253 VSTP instances.
253? That is such a specific number.
It is, isn't it?
Yeah.
And it's usually tied directly to the hardware, to the memory and processing power in the ASIC that's dedicated to running spanning tree.
So why does VSTP break down there? What's the problem?
The problem is that VSTP runs a completely separate spanning tree instance for every single VLAN. So if you're in a big campus with, say, 300 or 400 VLANs, which is not uncommon.
You've blown past the limit.
You've blown past it, and the switch will either refuse the configuration or just become unstable. MSTP is the solution because it lets you group hundreds of VLANs under a single instance, which is way more efficient. It's the definition of trading granular control for massive scale.
Another great trade-off example. Okay, let's shift to the really modern stuff. Packet flow and quality of service. In Junos CoS, there's a whole processing pipeline. Where in that flow do the rewrite rules get applied?
This is a great question because the timing is so critical. The rewrite rules are applied at the absolute final stage, on the egress interface, just before the packet physically leaves the device.
The very last microsecond. Why wait so long? Wouldn't it be better to mark it on the way in?
You could, but the whole point of a rewrite rule is to set the QoS contract for the next device in the path. If you marked it on ingress, some other internal policy on your own network might change that marking before it even leaves.
Ah, so you can't trust that the marking will survive the journey through your own box.
Exactly. By applying it at the very end, on egress, you guarantee the packet leaves with the correct DSCP or QoS value stamped on it. You're ensuring the downstream network, like your service provider, interprets your QoS intentions perfectly. It's the final stamp of approval.
Okay, final topic, and this one is right at the heart of modern data centers. EVPN VXLAN. EVPN uses all these different route types. We know type 2 is for AMSI addresses, but which route type is specifically for advertising layer 3 IP prefixes subnet routes between VTEPs?
That critical job falls to the type 5 IP prefix route. And this route type is, it's foundational to building a scalable layer 3 fabric.
So why is it so important? Can't the VTEPs just figure out the layer 3 routes using the layer 2 information from type 2 routes?
Well, they could, but it would be incredibly inefficient. If you only have type 2 routes, you have to rely on layer 2 flooding mechanisms like ARP to find remote layer 3 destination.
Which doesn't scale at all.
It kills scalability in a big fabric. Type 5 leverages BGP's power to distribute layer 3 routing information cleanly and efficiently across the control plane. It allows every VT2P to know about all the subnets without having to flood anything.
So it separates the routing from the layer 2 transport.
That's the key. It lets you build these massive, efficient data centers where routing decisions are made intelligently, not discovered through brute force flooding. It's a game changer for scale.
Thank you so much for sending in these sources and for trusting us to walk through this with you. Keep learning, and we will catch you on the next deep dive.